There are many different ways to measure electricity and many different properties of electricity. When we talk about electric potential, we're talking about stored energy that has the ability to do work. And we can measure electric potential with volts. Take a regular AA battery. Almost on any AA battery you can find around your house, it'll tell you how many volts that battery has in it. So basically, how much potential energy is stored within that battery. As you increase the voltage, you increase the potential to do work. What's really amazing is most of the outlets in your house that you plug your computer in, your phone charger, your blow dryer, your coffee maker, those are all typically about 110 to 220 volts. However, when we make an X-ray exposure, we're using volts up in the thousands, anywhere from 5 to 400,000 volts. And that's where the term kVp comes from. It's kilovolts. A conductor is any substance that allows electrons to flow easily. On this example here, there's a piece of copper wire, which is acting as a conductor. So what are some other conductors? Water is a conductor due to its salt content. Most metals around your house are also conductors. Voltage must be applied to the conductor for electrons to flow. For example, if you hold a pair of jumper cables in your hands, you won't get electrocuted. However, if you plug those jumper cables onto a car battery and then hold the other end of the cables, you will get electrocuted. That's because you've placed the conductor on a voltage source. We call this movement of electrons, we call it electrical current. So remember, this is critical. A voltage must be applied to a conductor in order to get electron flow called current. Just like we were able to measure potential energy in volts, we can measure current in amperes. The equation for an amp is 1 coulomb per second. And we learned that coulombs are a unit of electrical charge. So it's basically the amount of electrical charge traveling per second. Something that I find really cool, and it's really important for you to know now because it's going to become critical later, is that once you apply a conductor to an electrical potential, not only does it create a current of electrons, but it also produces a magnetic field. Scientists are so amazing that they can determine the direction of the magnetic force that was created when the conductor touches a voltage source. The mnemonic used to find the direction of the magnetic forces is the right hand grip rule. What you do is you would put your hand around a wire with your thumb facing the direction of current flow, or your thumb facing away from the voltage source. To demonstrate this, grip a pen or a pencil like what's demonstrated on the screen. Your thumb is facing in the direction of the current flow, and as your fingers wrap around the top of the pen or pencil, that's the direction of the magnetic field. So in our example, the magnetic field is moving away from you as it goes up around the pen or pencil, and then comes toward you as it makes its way underneath the pen or pencil. There are also some extra components that we need to talk about when discussing electricity. For example, an insulator. An insulator is any kind of material that prevents electrons from flowing. So besides this chunk of wood, what are some other insulators? Rubber, glass, clay. Those are all examples of insulators. Whereas an insulator prevents electron flow, resistance just slows the current. The more resistance you have, the slower the current will go. We're able to measure resistance in ohms. So as we increase resistance, we decrease current. And when we increase ohms, we decrease amps. The resistance in this coil of wire inside the light bulb is causing this light bulb to light. A semiconductor is a special material that fits somewhere between a conductor and an insulator. What makes it really interesting, as the temperature of the semiconductor increases, the resistance decreases. The most common example of a semiconductor is silicone, which is a part found in your iPhone, in your Android, in your computer. Almost any kind of electronic device has a semiconductor in it. The last unit of measurement I want to talk about are the watts. And the watts is the amount of actual power the electrons can provide. So you might be asking, what's the difference between watts and volts? Well, remember that volts are potential power and watts are actual power. So if you have 3 volts going at 2 amps, the total power is 6 watts. So how much actual power or watts do common household items need? Well, my coffee maker requires about 100 watts, my PC requires about 2000, and our x-ray machines, man, they require anywhere from 20,000 to 150,000 watts. God, that's incredible. The last equation I want to talk about is Ohm's law. Ohm's law demonstrates that electric potential equals current times resistance, or voltage equals amps times ohms. So Ohm's law is V equals IR. But you might be asking, why is I the symbol for current when the symbol for current is A for amps? Well, when this equation was developed, it was developed in Germany a long time ago. And at that time, amps was not the universal SI unit. The unit at that time was Intensitat, which translates to intensity. So try this practice problem here. We have a current of 0.5 amps, which passes through a conductor that has a resistance of 6 ohms. Well, what is the voltage across the conductor? So we use the equation V equals IR. So we have V equals 0.5 amps times 6 ohms. What does that give us? It gives us 3 volts. This is how I've remembered Ohm's law. Anytime I have to do this on a quiz or exam, I draw this triangle, I put V at the top, and then IR at the bottom. So let me show you how this triangle would work with the equation we just had. So in the example we used previously, we have 0.5 amps and 5 ohms. And so if we were to put it into this triangle, it would look like this. The amps would go on the lower left corner, and the resistance 6 goes in the lower right corner. So if you multiply across 0.5 times 6, the answer we get is 3. Let's try with different variables, 3 volts and 6 ohms. You put the 3 volts on top, the 6 ohms on bottom, divide 3 divided by 6, and you get, all right, one more. This time we have 3 volts and 0.5 amps. The 3 volts go on top, the 0.5 amps go below. 3 divided by 0.5 is 6, so we have a resistance of 6 ohms. You'll want to know all of these units here, as well as the equation for Ohm's law and the equation for watts.